Hi, in today's video I'm going to show you how to decode Base32 encoded data into a binary. My name is Karol Moros and you are watching Make Programming Fun Again. So first let me quickly recap what Base32 is and how to use it. So Base32 is a way of encoding binary data, which may contain any possible byte, into printable ASCII using an alphabet comprised of 32 symbols. And these symbols are capital A through capital Z, corresponding to the values 0 through 25. And then there are another 1, 2, 3, 4. There are another six digits, 2 through 7, which correspond to values 26 through 31. And these values are each symbol in the Base32 alphabet corresponds to 5 bits in the source binary. And so this way, every 5 bytes of the source binary correspond to 8 bytes in the encoded text. So the group of 5 bytes in the source or 8 bytes in the encoded text is called a quantum. And so an example of how Base32 works is if we use the Base32 command in the available in Unix on Linux, and we can see that it encodes the value I passed to it as Base32, and then for the remaining bytes it gave me equal signs. And the one issue with the Base32 command available in Linux is that it's usually based on GNU core utils, and it is GPL encoded. So if you want to use it in any commercial or proprietary code, you will be shooting yourself in the foot because it is GPL encoded, and therefore you may be hit with GPL, forcing you to also open source all of your code as GPL. And therefore we are implementing it from scratch, and also we are doing this to understand how it works. So with all this introduction, I'm going to quickly show you what we did in the previous video where I talked about encoding Base32. So we implemented a function called Base32-encode, and in the main function we passed a string to it and printed the result. So let me show you how this works in action. When I compile it and run the program, it prints a Base32 encoded string, and when I pass it to the Base32 command from core utils with the D flag for decode, it outputs the original string we have passed to it. So for now, this command is not very useful because it's printing a hard-coded variable. If we wanted, we could expand it to also be a bit more generic, but this is not the point of this video. We are going to use this with hard-coded data. So in order to do the reverse of the encoding process, we need to define some sort of an API, and we are going to need a function that's going to be able to return a value on success, or it could return an OK code on success, and it could return an error code on error, or we could return the number of bytes we have decoded, or an 0 or a negative value on error. But for now, let's just go with the returning the number of bytes decoded. So Base32 decode is going to take a pointer to a constant string and a pointer to the destination buffer and the size of the size of the destination buffer, so we can use it as a limit. And yeah, and also the error messages we are going to return from this function could be values something like base32, okay, and that would be, no, we're going to define only error messages, because on a correct execution this is going to return the number of values read. So if we did say that base32 incorrect padding is -1, or maybe like so, -1, then we can ensure that, yeah, this is going to be the value we are going to return on incorrect padding. Yes, great. So then in the implementation file, we're going to, no, wait. In the implementation file, I'm going to scroll all the way to the bottom, and we're going to write the implementation of this function. And then we are going to need some local variables. And for example, we're going to need n, which is going to be the total number of bytes decoded. And then we're going to need a destination index. Also, a disclaimer, my implementation is mostly based on the Go standard libraries implementation, and I'm going to be using the Go standard library as a cheat sheet. So you may see me switching to the Go standard library. And we also may end up exiting from the function early, but we cannot use the return because there will still be some cleanup data we're going to have to perform. So instead of just returning, we're going to set a value and use it to exit our loop. And in order to use the Boolean type, we're going to need to include the standard bool header file. We have reached the end of input. Okay, and then our main loop is going to look like this. While the source, the character in the source file is not a null terminator, and this means until we reach the end of the string, we can define a buffer, and every iteration of this outer loop is going to be a quantum we are going to define. So this is going to be a buffer, and then the length of the buffer is going to be 8 by default. But if we encounter a quantum that is not complete because it contains padding, for example, or if the input ends abruptly, then it's also going to mean that the length is going to be less than 8. And then we're going to write a loop to consume the source string, and we're going to consume up to 8 bytes at once. And we do not increment the I variable because there may be situations when we actually do not want to iterate by 1. For example, because we encounter white space, in which case we just skip over that character. And yes, so in here we define we get the next character in the string, so we dereference the source pointer, and we increment the source pointer so that it points to the next character. And if the character is in the if the character is a white space, then we just continue, and we need to include ctype.h in order to use isSpace. And then we can say okay, and then we in the buffer we're going to store binary values corresponding to the actual value we have encoded in the source string. And in the case and in order to get this value, we are going to define a helper function that's going to be called, and this is going to be since it's a helper function, it's going to be static, and I'm going to call it Base32-decode char, taking a char called C. And then in here, if C is between A and Z, then we return the distance from A, which is going to be C minus A. If C is greater than or equal to 2 and it's less than or equal to 7, then we return 26 plus C minus 2. And in any other case, we return 0, we return all FF, which means error value. So we can basically say if the C is the buff at index equals Base32 decode char, and if buffer at I equals 0xff, which means if it is an error, we can basically return an error, and we have not defined an error message for this use case, so I'm just going to say define a new one. The Base32 incorrect symbol -2, and Base32 incorrect symbol, like so. Also, before we output any data to the destination buffer, I'm going to zero it, to fill it up with zeros. And I'm going to use a function called memset. And this takes a pointer, which takes a value we want to fill it with, and then it takes the limit. And no, we're passing destination. Okay. And yes, it has the correct header files. So also, if the character is a null terminator, or if it is a padding character, then it means we have reached the end of the source, and that the length of the current quantum is equal to I. In which case we can break this loop, and if everything works fine, we can assume it's working fine. And then in the case if we have decoded all these bytes in a quantum correctly, then we're going to need to put them in the actual destination. And in this case, we are going to use a switch statement with fall-through clauses. So it means that if the quantum has 8 bytes in the source, it means we are encoding 5 bytes in the destination. And in this mapping here, oh yeah, this is not my, these are slides from the previous video. It's this one. So in this case, we can see that if we have 8 bytes in the source, it means that the target is going to be comprised of a 5 bits of the last symbol and 3 bits of the second to last symbol. So this is going to mean that the destination at destination index plus 4 equals buffer at 6 moved it's going to be moved 5 bits to the left, and it's going to be summed with buffer at 7, and we increment the counter n, and we in Go we do not need to include a fall through statement because it doesn't exist. A switch falls through the next cases if we do not include a break. So in this case we are not including a break, so I'm going to indicate that we fall through so that it is obvious that it's not a mistake. Then if we have 7 bytes in the destination, in the source, we can say that the byte 3 of the destination is going to be comprised of 2 bits of byte 7 of the source plus 5 bits of byte. This is byte 6, this is byte 5, and this is byte 4 if it's 0 indexed. So this is going to be this byte moved 3 bits to the right. This one is going to be moved 2 bits to the left, and this one is going to be moved 7 bits to the left. So destination I plus 3 equals buffer this is 0, 1, 2, 3, 4, 5. Okay, this is 4, and this is moved 7 bits to the left, and we sum it with buffer byte 5 moved 2 bits to the left, and we sum it with buffer 6 moved 3 bits to the right. We increment n. Now 6 bytes is not a valid value for an input. So if the dlen is 6 or is 6, it means that you have to return an error message. So I'm going to skip this case. Now 5 means that we have 0, 1, 2, 3, 4, but we can encode 3 bytes of the destination, which means in the case of 5, destination at the STI plus 2 equals, this is 4 bytes, so this is going to be moved 4 bits to the left, so that's, and it's buffer 3 moved 4 bits to the left, summed with buff 4 moved 1 byte to the right. Increment plus n. 4 is not a valid, is it? 4. Oh yeah, 4 is also valid. So case 4, dst di plus 1 equals, this is going to be byte 1 moved 6 bits to the left, 6 bits to the left, summed with buff2 moved 1 bit to the left, plus buff3 moved 4 bits to the right. And plus plus, in case of 3 the value is incorrect, in case of 2 destination dsti plus 0 equals buffer at 0 moved 3 bits to the right, summed with buffer at 1 moved 2 bits to the right, and plus plus, and at the end of all of this we increment the pointer of destination we increment destination index by 5. And after all of this we return the n, and here we are probably also going to need to handle incorrect values of dlen, which is 1 or 3 or 6 if I remember correctly. And then in here we're going to need to handle padding, handle and validate padding, like so. Okay, so let's see if this even compiles. It seems to compile. We won't see any difference in the output because we have not defined anything in, we have not modified anything in main. So in order to have some sort of a baseline, we could define some sort of a test string. So in this case I'm going to use the text hello. No, sorry, base32. And in this case, this example is it's actually behaving as if I have passed 6 bytes of input, because the output of echo contains a new line which I'm going to remove with tr. And this way we have this base32 encoded text, which I'm going to use in the main function. So let's say char encoded equals this, and then we can reuse the destination buffer, base32 decode encoded to destination with a limit of 80, and I'm going to take the result, and we can print out the number of decoded bytes, and we can print out the string that we got decoded. So destination like this, and now I am going to compile it and run it. Okay, we are getting another segmentation fault. And let me see what's happening. So okay, in this case I'm going to compile this with Clang. So I'm going to modify the makefile. Clang Clang, I'm going to use the Clang compiler and csflex-g, and I'm going to pass these CS flags in here, and I'm going to recompile it. And now I'm going to open it up in LDB. And wait, what? So for some reason now it's telling us it read 15 bytes, but this is not possible. Why is this happening? No, not this one. So again, the STI and okay, I'm going to put a breakpoint at line 95. So B main base 32. Oh, I can actually do it like so. Decode, and this is going to be line 55. Okay, well, it did not work. Base 32.c line 95, and I'm going to run it. Okay, what do we have in source? In source we have the correct string, and the okay, great. Next. So what's in C? C is the value. Okay. Next. What's in source? Source is correct. Next. What's buffer at I? Okay, it's 10. Next. Okay, continue. Okay, so maybe I screwed something up with the decoding part. Anyway, I'm going to quickly check if all the values are correctly decoded. So I'm going to put a restart it because I still don't know how to remove breakpoints. I'm going to put a breakpoint at base 32C line 123 and run. And what's DLN? DLN is 8. Okay, next. What's at buffer 6? Okay, what's at destination DSTI plus 4? What's in DSTI? Okay, I think we have not reset the STI value, so I'm going to. That's probably why we're getting garbage data, and it means I have to set n equals DSTI equals 0, like so, and maybe then it will work. So make base 32. Okay, and now we are getting the correct value. We are getting the hello value we have encoded in base 32, and we are getting the correct number of bytes. Now let's see what happens if we try a value that will contain it's longer and if it contains padding. So let's say echo hello world. We remove the trailing new line and we encode it as base 32. Okay, and now this contains padding. So I'm going to copy it and I'm going to paste it to the main routine, like so. Rebuild it, and oh well. It does look like we are caught in a in a loop. And why is this happening? Have we incremented this? Destination is incorrect. Yes. Are we handling padding? Okay, I'm going to open it up in LDB again and see what happens if we get run. Okay, we are what's Dylan now? Dylan is 0. What's in at DST? DST is hello world. And what's at source? Source is this. And why are we getting oh, because we are not breaking on end. Okay. Now if I recompile it and run it, we are getting a completely rubbish value. Okay, great. Bool end needs to be false, like so. Recompile it, and now we are getting a correctly decoded value. Great. And so it seems like this is already correctly decoding some values, and I'm going to use this moment to commit, because we are going to be we are possibly going to break something later on. So I'm just going to say naive Base32 decode implementation. And next I'm going to look at the Go standard library implementation, because it contains ways to handle incorrectly encoded data. So for example, if we have this means that if we have encountered the end of a string and there is no padding, and I'm not going to allow no padding implementations, because we are just going to, for the sake of simplicity, we are just going to assume that we are using the standard Base32 encoding and data must be padded. So this means that if we are in here and we encounter no padding, it means we have encountered corrupt input, which means yes. So this means if we encounter the end of a string, if this is the end of a string, we have encountered the end of we can just return Base32 incorrect padding. Okay. Then if the input character is a padding character, and we are at a dlen of 2 or more, and the remaining length of the source is less than 8, it means that we are going to get padding. Okay. So in this case, I'm going to calculate the length of a string in here. Size t length equals string length of the source, and if the current character is padding, and if we are at position 2 or greater, and if the length is less than 8, it means that there is padding. And okay, I'm just going to copy this and then we can try to wait, and you can just try to port it like so. Okay, so if length plus I, and I'm using a different name for a variable than they have in the source code, is 8 minus 1, which is 7. If length plus I is less than 8 minus 1, it means that there is not enough padding, which means that we can return base32 incorrect padding. And then for j, int j equals 0, j is less than 8 minus 1 minus I, j plus plus, and it says if length is greater than j and source at j does not equal padding character, then it means we have encountered incorrect padding. And then we can also handle the incorrect d length. And how and where? Okay, so d length equals I and equals true, and if d length is equal to 1 or d length is equal to 3 or d length is equal to 6, it means that the length of the quantum is incorrect, in which case we also can return an incorrect padding, because why would we return meaningful error messages, right? And if everything else fails to destroy us, then we break the outer loop. Okay, and now we can remove this Go implementation and see if this handles padding correctly. So I'm going to recompile it and run it, and it seems to still work. And let's see what happens if in the main function I'm going to I'm going to remove some padding, or I'm going to add some more padding. Oh well, okay, it handles too much padding. Does it handle too little padding? Yes, it does handle too little padding. It does not handle too much padding, but I guess it doesn't really matter. At least we can handle if there's too little padding. Okay. And if you have made it this far, then congratulations. You have just watched another Make Programming Fun Again video. I hope this was fun. If it was not fun, please tell all of your friends why this wasn't fun, and please tell me as well. And if you did enjoy this, or if I did actually show you something useful, then please consider liking and subscribing, because this helps a lot with the YouTube algorithm. And if you know why and you may, if you have any experience with authentication, then you may know that the reason I'm teaching you Base32 is because in the next video we are going to be talking about TOTP, which is an exciting topic in and of itself. In and of itself. So stay tuned, and I hope you learned something. Goodbye.